So, couple things before we totally fully begin. One, you need to be aware. We are having a test next Thursday. Test next Thursday. Test is when? Test is when? This is the test that's 80% of your grade. This is the test that's 80% of your grade. Second thing, I think I have not done a very good job of communicating with you peeps, so I'm trying to make it better right now. Some of you have realized that on Canvas there have been places for you to input your scores for your homework. And really you're not putting input a score, you're just saying, yes, I certified that I did all those things. I did all the homework. I understand. I have no questions. I use good, proper notation. Yes? So, some of you have not. Some of you have not. In other words, what I'm trying to say is some of you haven't put anything in. And I'm hoping that that's not true. Like, I hope that you have more done than nothing, because that would be really detrimental to your understanding and grade and everything else. So, what I've done is this. They have some due dates on them where they closed. I opened them all back up until Friday. So, all our previous homeworks from the very get-go in the beginning are opened up till Friday, okay? So, what I need you to do is you need to go on and you need to put on there, yes, I did it, or no, I didn't. And the sooner, the better. Okay? The sooner, the better. I'll probably try to update Skyward tomorrow. So if you guys can get it done today, that would be really good, because then you can kind of see where you're sitting just with your assignments. But remember, this test coming up, which is when? Thursday is 80% of your grade.
You said 50% of us are going to get 50% of that.
Well, I mean, what I'm saying is that there's a good chance that some of you will get really bad grade on it. And if that happens, then there are retakes available, and that's why we're doing it early enough so that we still have a couple weeks before the end of the term so you can retake it. Does that make sense? To help you get prepared, I have 2 practice tests that I'm going to hand out to you right now. So, pink packet is the homework for today. Come Friday, no homework. Reviews, practice tests. Next Tuesday, no homework, practice tests. Thursday is the test. Okay? So I'm going to hand out your practice tests to you. Here's the deal. If you take these practice, there's no answers to the practice test, because you kind of have to get that feeling of, I got to do these, and I'm going to see what I get. You understand what I'm saying? So no answers to these. I'll get you the answers later. If you think that you've seen these problems before, there is a possibility that you have seen these problems before, because it's kind of like Mr. Smith went through and he found the best of the homework, and he put it on here, then plus some others. Here's something that you really also need to be extremely aware of. Please, 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 please do not think that if you just memorize the format of this test, that the original test or the test that you're going to take, please do not believe or think that it will look just like this with changed numbers. It won't. You're going to take these 2 practice tests, and you're going to look at them and be like, these 2 things don't look anything alike. It's exactly right. And when you come ready to take the test on Thursday of next week, it won't look anything like these.
How are we supposed to know how to do it?
So this is where really, truly understanding the idea is coming into play, Kyla. You really, truly need to understand the ideas and not just be like, oh, it's this type. Oh, it's this type. Remember I told you there's like thousands and thousands of different types that there could be. There's no way that I can get you there, and you don't want to memorize. Now, also remember, Also remember, I have given you a white sheet. Did I also give you a yellow one? Or just the white one? For notes. I gave you the one with the sheet protector. And again, gave you a goldish one. Well, okay, yeah, the gold. Okay, so this one for sure, this is what I would say, I would have this mesmerized. Was it blue? Yeah, blue. So those, I would have, so those, like no notes are allowed on the test. You can't have any notes on a test. But just understand, if you just think you want to go to memorize, just memorize it, like, that's not going to help you either, right? You got to understand what it is that you're memorizing. Do you understand what I'm trying to say? Like, don't just be like, okay, F prime has an inflection point when F prime changes concavity. Okay, F prime has an inflection point when F prime changes the concavity. F prime has an inflection point when F prime changes concavity. F prime has an inflection point when F prime changes. Okay, I know that F prime has a critical point when F prime changes concavity. Sweet. What the freak does that mean? Well, I don't know. But I know it. But I don't. That's not going to help you. Do you guys kind of understand what I'm trying to say? Okay. Excellent. Perfect. So, today we're going to talk some more. Yes, Matthew. Sorry. That's a good question. I'll let you know. I would think 60 minutes probably would be a decent time constriction to think about. That's what I would think. But they are, again, just practice tests. But maybe try 60 minutes and then then you can be like, okay, then I'll circle things that I do after 60 minutes. Yes, Sarah.
So, is like the test that we're taking on Thursday, is that a time test?
Yes. Well, so it is a time test because I think we're just going to give you the time in class. If you don't finish, don't finish. That's what I believe. Because the AP test is timed. That's the one thing about the AP test. It is timed. So we have to learn how to manage our time. So it's kind of it's all kind of in one. Does that make sense?
Yeah.
I'm not trying to be mean. 25. 25 questions. Eric. They're all multiple choice. This first test, they're all multiple choice. Which, again, a lot of kids at that point go, yes, right? Just understand, every single answer has been crafted to look good. Every single one. So there's no way that you'll read it and be like, oh, I obviously know it's this one. It's going to have to be something where you actually go, let me read this. And here's another hint. It is timed. The test is timed. But take your time when reading the instructions because that's where a lot of kids go into like a little autopilot mode. They'll start to read an instruction and think they know exactly what's going on. And the problem is you don't. Or like you'll make one little mistake on the reading. So just make sure that you read it correctly. Does that make sense? Just be careful. Folks, I'm not trying to scare you to death and make you go like, Mr. Ugly! Okay, I'm not trying to do that. You guys are very, very smart. Every single one of you in this class is extremely smart. And you're all working hard, which is great. So, we just are taking it to another level. Do you understand what I'm trying to say? We're taking it to another level. So, you do have to do some things on your own. Go ahead and I think the first one we're actually going to look at is number 3. So, go to number 3. It's going to be the first one we look at. And how come, I think I'm going to have to go back down. I like the width thing, but I think I'm going to have to go back just the best fit so I can see a little bit better. Okay. Let me make sure I didn't have any. Sorry. Nope, I lied. I'm going to number 2 first. Going to go to number 2. Now remember, if you catch me today ever saying the word it, you get a ticket, right? Okay? So, as we read number 2, so we're going to look at number 2. Again, you can see up here there's a date, 1986 or something, 1988. That is from then the 1988 AP test, and it was number 8. Okay? It says the graph of y equals f of x is shown in the figure above. Don't let this y equals f of x concern you. It just means that y and f of x, you can write it as y equals, you can write it as f of x equals. It is the same thing. It's shown in the figure above. On which of the following intervals are dy dx greater than 0 and d2y over dx squared is less than 0? So here we go. Here's something you do need to memorize. Right here, this is f prime, and this is how you write or how they denote f double prime. You kind of already figured that out, right? It was like something, it wasn't totally like, kind of figured that out. So here it is. Talk among yourselves for just about 30 seconds. On what intervals are f prime greater than 0 and f double prime less than 0? Jamie? Did we learn it last class? So this would have to do, okay, that's an interesting question, Jamie. We have talked about Danica's chart, and we did that 2 times ago, right? Yeah. Danica's chart, we introduced Danica's chart 2 times ago. So we did more of Danica's chart last time, and we talked more last time. To say if it's what we learned last time, we learned a lot of things hopefully every time. We just applied more of Danica's chart to what we got. So take Danica's chart and apply it to this. This is the graph f of x. This is the graph f of x. The question is, over what intervals here is f prime or dy dx greater than 0 and f double prime less than 0? Talk to your neighbors. You got about 30 seconds. 30 seconds. Talk to you already got it? Everybody know it? Did you guys talk to your neighbors? Did you ask them? Did you tell them? So it's like, I think I got it. Did you ask Zach? Zach, did you say, Zach, what'd you get, man? Well, then help him. Spencer, you got it. Help him. How about you, Jacob? Oh, you don't have that paper? Let me get that for you, bro. Let me get that for you. Let me get that for you. So you want that to go in there. And there it is, my friend. Okay. Do we have it? Okay. B. Okay. So, Kyla, why? Why is it B?
Okay.
Do you want to try? You want to come and show, or do you want? Okay, come on up.
Yay! Go Kyla! Woo! Because f prime when it's increasing is positive, so it's increasing up until here. That means it's positive. And then acceleration is negative when it's decreasing. It starts decreasing here up until here, negative. And so that's the only section where it meets the whatever they're called, and so it would be B, I'm pretty sure.
Okay. So tell me how you got that the acceleration was decreasing from B to D. Just wondering. I'm just wondering.
Well, because it has to be concave down for acceleration to be negative, and so right here's the point where it starts switching and becomes concave.
And what's that point called?
Inflection or critical or
Point of inflection. Yes, different than a critical point, actually. And we'll try to get those straightened out in our heads. But yes, good. Ticket. So, point of inflection is here, which means it goes from the function, not it. You guys could have caught me and got a ticket, but you didn't. The function f of x goes from concave up to concave down. And at the point where the function goes from concave up to concave down is called the point of inflection. And so because the function is concave down, that's where the second derivative, or the f double prime, is negative, which is the stipulation. F prime is greater than 0. F prime is greater than 0, which means it is positive when it is increasing. So just like Kyla said, from here to here, the function's increasing. Notice how I said the function. The function's increasing from there to there. And the function, almost said it again, I know. It's so hard. The function is concave down from B to D. So the only place where it's happening both places. Cake tickets. See, I'm giving you guys options. Come on. Get them. So the only place where the function is both concave down and increasing is from B to C. There it is. Bam, shazam. Woohoo. Let's go. Did I forget circle B? B. Okay. Number 3. Look at number 3. Look at number 3. Look at number 3. A polynomial P of x has a relative maximum at negative 2, 4, a relative minimum at 1, 1, a relative maximum at 5, 7, and no other critical points. How many zeros does P of x have? So, couple things that you do need to know about a polynomial. A polynomial, oh yes, grab one, each of one of those. So, we're working on the pink one right now. The yellow and the blue one are practice tests. Our test is next Thursday. So, a polynomial, something that you need to know about this is a polynomial is always differentiable. I don't think we've actually used that word, so I'll write it up here. Differentiable. Okay? Last time we talked a little bit about it. And so we'll talk a little bit more. But we didn't necessarily use the word differentiable at the time. So a polynomial, if it's a polynomial, every polynomial is differentiable. Every polynomial is differentiable. And every derivative of a polynomial and second derivative of a polynomial is differentiable. Just know that. Okay, those are kind of key things to know. Not necessarily for this test, but in general. Sarah. So what does that mean? Ms. Ruthie, would you please tell us what that freaking means? Yes, I will, and for some reason I don't have my pink paper. I just make sure. I want to make sure I'm telling you guys all correct things here. So I want my pink paper. So, differentiable means this. First of all, it means that I can take the derivative at every point. Okay? And what that means is since you can take the derivative every point, it also means that you can find the tangent slope at every point. So, you take the derivative at every point, you find the tangent slope at every point. Last time we kind of talked about it this way. I can't remember the word we actually used last time. I don't think it was differentiable. We did say this, though. We said that it has to be continuous. We said for a function, how did we say it? We said for a function, for f prime to exist, then, so it's kind of like this. Right, so if for f prime to exist, what does that mean? That means the derivative exists, which means it is differentiable. So those are words that mean all the same thing, right? F prime exists if, or we say that we can take the derivative of f or we say it is differentiable. If the function is differentiable, you guys could have got another ticket. If the function is differentiable, if you can take the derivative at every point of the function, and you can find a tangent slope at every point of the function, which also means we also said it has to be continuous, right? Has to be continuous. We also said that it cannot have any ticket. Thank you. Finally, good. That the function does not have any corners, right? The function has no corners.
So are these qualifications for the function to be considered differentiable?
Yes. Yes, differentiable. I know it's such a hard word to be honest. Differentiable. So these are qualifications. The function has to be continuous. The function can have no corners. And the function can have no tangent slopes.
So if it meets all those qualifications, then you can take the derivative at every point.
Yes, take it. So if the function meets each of these criteria here, then what that means is the function is differentiable, which means you can take the derivative of every point of the function, and you can find a tangent slope of every point of the function. Yes.
But I thought that for the function to be differentiable, it has to have no tangent slope.
Tangent slopes have to be defined. It can't have a, sorry, did I say tangent slope? No. Vertical. My bad. That's going to be a full class ticket. Yeah. We want no vertical tangent slopes. My bad. No vertical tangent slopes. No vertical tangent slopes. Thank you. You guys caught me. I love it. Love it. So, let's answer number 3. A polynomial p of x has a relative maximum. So, I don't feel like I did a great job as a secondary 3 honors teacher last year teaching this concept of maximum and minimum. So I feel like I need to make sure that your teachers were better than me, or if I taught you, I'm sorry and I need to be better, so I'm going to help you out right now. If we look at a maximum or a minimum, what does that mean? Who can tell me what does it mean? Yes, Zach. Good. Ticket. What is an so be careful. Inflection. When we say inflection, we actually mean point of inflection, which means it changes from concave up to concave down. So not quite inflection is the right word, but I love the try. Eric?
It means like it doesn't go any further than that point at that area.
Ooh. Ticket. Only if it is a global or absolute min or max. Only if it's a global or absolute min or max. So we're going to talk more about that. Leah? Ooh, ticket! And what does critical point to us mean? Ticket again! Yeah! So, tangent slope is 0. It's a critical point. There's another thing that we want to talk just a little bit. I want us to understand a little bit more. So, Sarah, you have something you're going to maybe add? She said it? Ticket! For letting her say it then. So, here's the deal. A function has a maximum if the function goes from an increasing to a decreasing state. So if the function goes from increasing to decreasing, that's a maximum. A function is has a minimum if the function goes from a decreasing to an increasing state. Think about it. So what I'm saying, if I go from an increasing to a decreasing state, that creates a maximum. If I go from a decreasing to an increasing state, that creates a minimum. So, good question. Like, what is this extrema relative extrema mean? Good, great question. In all reality, it's just an English word that is for, like, min or max. It means min or max. It's like a relative min or max. And what does relative mean? Relative means the same thing as what's called local. So I think your teachers hopefully taught you about local, and like Eric then said, we also had global or what's called absolute. So relative and local are the same. Global and absolute are not local or relative. Here's kind of the deal, though. To be honest, there's debates in the mathematical world. Okay? And what they're saying is that every minimum or maximum or every extrema is relative or local. Only some of them are both local and global. Think of it kind of like Walmart. Okay? Local. Do we have a local Walmart here? Yeah, it's just right over there. But yet we also know that Walmart is a global organization. So there's both local and global of Walmart. But then take, say, the Purple Turtle. Well, Purple Turtle has sweet milkshakes, right? We love them. However, the Purple Turtle is only local. There's not a global Purple Turtle. Does that kind of make sense what I'm trying to say? So as we look at extrema, or as we look at mins and maxes, every single one of them is considered local or relative, but then there are some that will be global or what are called absolute, because they will be the absolute or highest or lowest point of that function. So when you kind of said it won't go any higher, maybe I misunderstood you, but I kind of took that as you were meaning global max in that relative area. Okay, yeah. So as the function then increases, at some point in time it's going to start decreasing, and in that relative area, then that is a maximum. Yes.
So, like going back to like the Purple Turtle or whatever, would that also be the global minimum too, or like maximum? Like if no other point was like lower than it, even though it's not like a low.
Okay, so I'm just trying to help us understand the difference between local and global. When you think, you're okay. When you think of global, absolute sometimes is a good word too, because absolute would mean the absolute highest point of our function or the absolute lowest point of the function. So I drew this up here, right? The deal is you could have a function that looks like this. So this point right here, it went from an it. I tell you, man. You guys could have been earning gazillions of tickets today. As the function here increases, it goes ticket. The function goes from an increasing state to a decreasing state, which means this is a maximum, and it happens to be local. Now, they're all local, but we also know that this maximum of the function is not global because the function goes higher. The function goes higher. So that point right there is only a local max. This point right here on the function is only a local min. Does that help understand or clarify the difference between the two? Jamie?
How will you label multiple locals?
Well, how would you label them? You would just say, like, the local min, like if this graph did something more like, the function looked like this, I don't know, whatever, like that, and you had multiple local mins, you would just say the local minimum is this value, the local minimum is this value, the local minimum is this value. You could just say local min, and you could state them. I'm pretty sure. I'm gonna have to ask my math geeky friends, and I'll ask them. but I'm pretty sure you can just list them. Local mins. Okay? So, back to this point. Sorry, my bad. Back to here. We learned so much. Here's the deal. We learned so much from just one problem, don't we? That's what the AP writers do, though. They take one problem and they may ask you such different parts of it, but yet it's all in here. So, that's why one problem sometimes expands. Take a look. So, a polynomial has a relative maximum at point -24. Mr. Smith doesn't do this, but I don't mind doing it. I don't mind putting up a graph. He always puts points. I'm like, dude, that's cool, but I don't think I could do that. So anyway, I don't do what he does on this. I'm so sorry. Here we go. I am a rebel. Mr. Rusty, rebel without a cause. Yes. Okay, -2, 4. So -2. 4. Now sometimes I won't be able to just like put nice dashes here because they might say something like -250 and 586. So I just have to kind of maybe say, okay, it's -250 and it's -586. Actually, and I did that wrong, so that's a full class ticket. No, I didn't. I did it right. -4. You understand? Okay. There's a relative maximum. What does that mean to us? Well, that means relative maximum means the function went from an increased state. So it looks something. I could have got. Hey, come on, guys. You get me. Come on, the function. Because if you say it on the test, the AP writers will mark it wrong. It is not defined. They're just saying, we have no clue what you're saying, and they'll just go like this. And you just missed a whole bunch of points because we didn't focus on that little piece right there. The function then looks something of that nature. Would you all agree? I mean, I'm not sure exactly how it looks, but something of that. The function went from an increasing to a decreasing state. So, here we go. Here at the point 1, 1, the function has a relative minimum, which means the function went from a decreasing to an increasing state, something like that. Does everybody agree to that? Hey, Kipper! Dude, dude, I love the mask, man. I'm digging that. I'm digging that, man. It could be old, and if it's old, I understand all the colors, but you know. Oh, baby! Oh, baby, it is. I tell you what. Oh, where does it go? Limit. We're limited. Okay. See you, brother. Okay. Now, it has a relative maximum at 5, 7. So maybe I'm just going to say like that's 5, right? 5. You guys could have caught me on it. The function has a relative maximum at 5, 7. 5, 6, 7. I won't get offended, I promise. So at 5, 7, the function has a relative maximum, which means it's going from increasing to decrease. It looks something of this nature. Correct? Let's find this out now. So, we said, I told you at the beginning, every polynomial is differentiable, which means that it, come on! Ticket. So, the function is continuous. The function is continuous, which means there's no breaks, right? There's no discontinuity. So, Kyla, you're absolutely right. This is going to connect. This is going to connect. The function is going to connect to each other. Then the function will continue down somehow. And over here, the function must also continue down. I know, since it says There's only these three. It says there's no other. And Leah said earlier, a critical point is when the ticket tangent slope is 0, which means there's a critical point, there's a critical point, and there's a critical point. Or in other words, there's no more minimums or maximums on this function, which means this graph will not turn and go back up because there would have to then be a critical point. So it must go down. This one can't turn and go back up because it has to be a critical point.
When the global minimum of the graph is negative infinity, do you say it doesn't exist, or do you say it's negative infinity?
Great question. For there to be a minimum or maximum value of the function, it has to actually approach a specific value. So when we say negative infinity, does that really approaching a specific value? So there is no global at negative infinity, or there is no global at infinity. Does that make sense what I'm saying? Good question, Eric.
So would the global minimum and maximum of this graph be for the minimum 1, 1 and the maximum 5, 7?
Ooh, so the relative. But the deal is, the question I have for you, Eric, is are there points that are lower than this point right here on the graph or on the function? If that's true, this is not global. It can only be local or relative. However, 5, 7 here, this would be a global maximum or absolute because this is the highest point of this function. Does that make sense? Good call. Good observation. Love it. There's also a relative maximum right here as well. Now, answer the question. How many? What is a 0? Excellent. Good. Where the function crosses the x-axis. Tick it. Where the function crosses the x-axis, because it's where the function has a y value of 0, and all along the x-axis, the y value the function has a y value of 0. So how many zeros are there going to be? 2. Go ahead.
Hypothetically speaking, if the relative maximum of 5, 7 was instead a removable discontinuity, what would be the global maximum for this graph? Would it be the discontinuity, or would it be the actual number?
Ooh, good question. If it was removable, it wouldn't be a polynomial, right? Because it wouldn't be differentiable at that value because it was removed. But
Maximum and minimum only applicable for differentiables?
I have to ask that question. By the way, somebody asked this question last time. Point of inflection is, what is the tangent line equal to at the point of inflection? It kind of depends. In other words, as I look at this graph right here, the point of inflection is like about right here, correct? But as we look at it, we can still see a slope, right? It's not vertical. We still see a slope. If the graph was even more spread out, the tangent line is whatever the tangent. It doesn't have to be vertical. Yeah. Does that make sense? Now there could be if it was kind of really tight. If it was really tight, extremely tight, and looked something more. Let's see. Like that, then as you look at that, then you could say, oh, well, that tangent line is vertical, which means then it would not be differentiable at that time. Or we would say then the derivative would not exist. Does that make sense? You hearing here?
So, isn't it the inflection point when the tangent line starts being on top of the graph and below the graph?
So it is true, but as I was talking this through with Mr. Smith, and he was just telling me, he said, look, the more and more you zoom in on it, you can still see that this line doesn't go to a vertical line. It's just there. So the tangent line at that point is still there. It's not undefined. It's still tangent line of that point. Because, again, looking at it from just a bunch of points on the graph, just a bunch of points on the graph, it's just a point. So then the question is, we're going to take another infinitesimal point right next to it, and I'm looking at that tangent. Do you see what I'm saying? So we're looking at points infinitesimally close to each other, and then we're finding the slope of the line that's connecting those 2 points. Well, even if as I go through here, so even if I put those 2 points infinitesimally close to each other, it's still going to just be a positive. Here it'd be a positive, right? It wouldn't go vertical. Even though they were infinitesimally close, it wouldn't go vertical. It's still just a positive. Now, again, here if we go infinitesimally close, and that's like straight up and down, then that would be vertical. Here, then here, then here. Uh-huh. Ooh, so let's go back to maybe what you just asked a second ago. You said on a function. So you got to be careful, right? On a function, that would not be possible because a function says for every input there's only one output. However, we've seen graphs, right, where they do weird things. And so I think the simple answer to your question, if you're looking at it just from a function standpoint, the answer would be no. But if you're looking at it from saying, oh, well, this f of x graph, then the answer is yes, possibly. But the tangent slope, I don't think, at that point in time, I think, and I'd have to maybe talk this through with Mr. Smith or Mrs. Lyons, Mrs. Summers, would be kind of more, the tangent slope would not exist at that. I don't think the tangent line would exist on that F graph. Leah.
So the inflection point is pretty much just like the greatest slope of the position to that area, right?
Yes. Usually the inflection point will be the greatest slope, but it doesn't necessarily mean that it is vertical.
And then like with the having it go back, like for position versus time,
Mm-hmm.
you can't really go back in
Ah,
time.
we talked about that last time a little bit. I don't know if you remember. We did talk about that. Good morning, Anarchy speaking. Hey, Judith. Okay, I'll send her down. Bye-bye. Kyla, they need you down in the main office. You will be returning, though, that's a good thing. That's a good thing. So, you will return. So, Leah, we talked about that a little bit last time because you guys asked this question about time being negative, and I said, well, time in essence is kind of really just relative. Time is just relative, though. Time is relative, right? The particle could have started wherever, and we're saying, okay, this particle could have been in motion since the dawning of time. And we're saying, well, okay, we want to start time now. But where was I a second ago?
That would be negative time though.
But so your question was, though, you asked that, you just said time can't be negative.
I'm saying like time you can't like go back as in like from 5 seconds to 4 seconds like that. Yeah, you can't. Like because you can't like turn it in on itself and everything.
So there again, I think so. We have to be careful. These are great questions, and maybe they're a little bit more beyond my realm of understanding. And I understand what you guys are saying, and you're trying to make it fit, like you're trying to make it make sense. I love it. Love it, love it, love it. We do have to say, let's keep maybe to the things that are going to be more on the test, towards the test, if that makes sense. Is that cool if we do that? So, Jamie, you had a quick question, not so quick question. Okay. If you remember, let me know. Let's take a look at number 4. Number 4. Let's look at number 4. Okay. So here we go. Sometimes you'll be given, like, in this question, all honesty, this question was a calculator section question, so they didn't give you the graph. Mr. Smith put the graph into this because he wanted to just not have you worry about the graphing part right now. We'll get to the graphing part later. This is just not worrying about the graphing part right now, okay? So it says, let f be a function defined for all real numbers x. And up here, you'll notice it says f prime of x. If f prime of x equals this, which is this graph, then f is decreasing on the interval what? So, what do we know about the relationship between f and f prime? Correct. When f is decreasing, f prime is negative. So, where over here is f prime negative? Now, I'll be honest, this kind of got me a little bit. So I was like, well, okay. Notice how it kind of just continues this way here. So this is going really to where? Negative infinity, right? So we have negative infinity. And then the question is, like, when I first did this problem, I actually just thought it should be negative infinity to negative 2 because what happened right here? It hit 0, and is it negative or positive at that time? It's not. So I kind of thought, oh, this should be negative infinity to negative 2. This I'm telling you what I thought. However, it's still negative over here all the way up to 2, correct? So reality, what happened here? What happened here? What happens when the f prime or the tangent slope is 0? Okay, so it's not necessarily undefined, just the tangent slope is 0, right? So the graph maybe it was doing something like this of f, just throwing it out there. Maybe doing something like this, and maybe it kind of went here, and then it went continuing down, correct? So in other words, like right here, the tangent slope kind of became pretty much 0 right there. But if I were to say over what interval is this thing decreasing, I would continue all the way to here, correct? So in other words, it's going to be from negative infinity to 2 that it is decreasing. That's an infinity sign. Negative infinity. And why? Because f prime is negative, it will be decreasing. So even though at this point right here it hits 0, it just means at some point in time this kind of flattens just for a second. Yes, this is the f prime graph. Okay? So again, the answer to that then would be A. Okay, now go to number 8. Oh, Jamie? So at some point, at what point? At negative 2. At negative 2 time, that graph flattened.
Just that one point.
Correct. And at that one point, the tangent slope then became 0.
This is weird, because normally I think that is
But remember, the tangent slope, when I look at the tangent slope, we're taking 2 points that are infinitesimally close to each other. So it doesn't have to, it's not like it flattens real. It doesn't do like this thing here. It's just for a bleep second. Beep. It's crazy. I know. You guys are good. Okay, go up to number 8. Go to number 8. Let's take a look. The graph of the function f shown in the figure above has a vertical tangent at the point 2, 0. So, the graph of the function f shown in the figure above, so this is the function, has a vertical tangent point at the point 2, 0. Right there, that's a vertical tangent point. And has a horizontal tangent, to the points 1, negative 1. So at 1, negative 1, there's a horizontal tangent, and at 3, 1, right there. For what values of x from negative 2 to 4 is f not differentiable? So go back to that definition. What does it mean to be not differentiable?
Continuous, it needs to be continuous, have no corners, and have no vertical tangent.
So is there any place here where it's not continuous? Where?
0.
At 0, it's not continuous. Also, it can't have it. I said it again. The function can't have vertical tangents. Where does the function have vertical tangent? At 2. So our answers are 0 and 2. Go to 9. Be careful here. Be careful. Here's a place where there's a good example of the writers messing with your brain a little bit. The graph of a twice differentiable function f is shown in the figure above. Which of the following is true? So, what graph are they showing you? What does twice differentiable mean? It means f. So it means that f can be differentiated twice, correct?
So it's not the derivative, the second derivative, it's saying that the tangent.
So what graph is this? This is the graph of f. This is the graph of f. This is the graph of f. It's saying the graph of a twice differentiable function, which means f can be differentiated, or you can take the derivative twice on f, but that graph of f is shown above. So be very, very careful. You just got to be very, very careful. The graph of a twice differentiable function. So what are they telling you? The graph of a function that can be differentiated twice is shown above. Which of the following is true? Okay, immediately go to the chart. So yes, ma'am. It means you can take the derivative, which means that the tangent slope exists. Which means it's continuous. The function has no corners. The function has no vertical tangents. That's what differentiable means. So which means you can take the derivative, or it's differentiable to be the first one, and then you can do it again. It means you can get f prime and you can get f double prime. Yep. We'll talk about that later, but yep. So let's talk about what this means. Now, again, I just sat in on a class with Mr. Smith, and he said over his 14 years of teaching AP Calc, he's learned a little trick. So I'm going to give you guys this little trick that he learned because he gave it to his class. So I'm going to give it to you guys. Is that cool? Anytime the answers are in this format, something less than something less than something, over the last 14 years and all the problems that he has looked at, the AP Calc teachers, or not the AP Calc, AP writers, have always looked at it being this. The first one will be negative. The second one will be 0. The last one will be positive. Now, that doesn't mean that they couldn't write something where it was negative, a little less negative, and either a little less negative than that, or 0 or positive. But he's saying over the last 14 years, and how many problems he's looked at. I'm just saying, do you guys understand how many problems he's looked at? I don't think you guys really can truly comprehend how many problems Mr. Smith has looked at and done. So he's saying if the answers are in this format, something is less than something less than something, you're looking for the first one to be negative, the second one to be 0, and the third one to be positive. So the question really is, what is f of 1? What is f prime of 1? And what is f double prime of 1? Because if we can figure out what these are, we're looking for this kind of idea. So at f of 1, here's my function, f. At 1, what would you tell me that f of 1 equals? 0. Okay, so I've already determined that f of 1 should be in the middle. F of 1 is in the middle. So if f of 1 is not in the middle, it's not one of my solutions. Do you see that? Now look for f prime of 1. Well, how does f and f prime work together? If f is increasing, it is positive. So what's going on here? Increasing, so f prime of 1 should be positive. That means f prime should be first. So therefore, we already know the answer. We know that f double prime, if it's concave down, then f double prime is negative. Look at our function here. What is it? Concave down, which means this is negative. Okay, we didn't get through as many as I wanted to. I'll try to get some more up. Have a great day, folks. Good work today. Great questions. You're welcome. We're going to see. Hopefully this QuickTime thing worked. Yes, put it right back here. How far did you get? A little bit?
I think the last name I did was like Jansen or something.
Good for you. Let's see if this worked, dude. I'm going to hope and pray it worked. Yep, have a great day. Oh, yes. Yep, I will be. See ya. Have a great day. Yep. Good work today, folks. Good work today. AP Calc. Let's see. Maybe let's just do it by date. September. Was today the 16th? Was today the 16th?
Yes.
Yes. Okay, have a great day, guys.